Hello everyone, I'm going to talk about the paper Taming Transitive Redundancy for Context-Free Language Reachability. Briefly speaking, this paper improves the efficiency of context-free language reachability by reducing the computational redundancy caused by transitive relations using a partially ordered algorithm running on a hybrid data structure. Let's start with the background. Context-free language reachability, also called CFL-reachability, is a fundamental framework for program analysis. It has been widely used in shape analysis, data flow analysis, type state analysis, pointer analysis, and so on. A CFL-reachability problem is to determine whether specific sourcing pairs in a given age-labeled directed graph are connected by a reachable path. Here, a reachable path is a path whose age labels form a string, which is accepted by the given context-free language. Formally, a CFL-reachability instance is comprised of a context-free grammar and an age-labeled directed graph, where the grammar is comprised of an alphabet, some production rules, and a star symbol, and the alphabet consists of terminal and non-terminal symbols, where a non-terminal can be induced from other terminals or non-terminals by the production rules. For example, in a production rule x equals yz, x is a non-terminal and yz can be terminals or non-terminals. In the graph, a path from a node v0 to another node vn indicates an x reachability relation from v0 to vn if the age labels form a string from which the non-terminal x can be induced. CFL-reachability is solved by deriving and inserting new ages to the graph under the guidance of the context-free grammar. Specifically, if a path from Vi to Vj indicates an x reachability relation from Vi to Vj, an age Vix Vj is derived. And if the newly derived age is not already in the graph, it's added to the graph to make the x reachability relation explicit. Here is the standard CFL-reachability algorithm, which is also the most widely used in practice. The algorithm maintains a work list W to hold all the unprocessed ages. Initially, all the ages in the graph and all the underlying self-cycles are considered as unprocessed. While solving reachability relations, the algorithm iteratively pops an age from the work list, processes it, and adds the new ages into the graph and into the work list, until the work list is empty. Specifically, the algorithm will derive new ages from the age being processed and its adjacent ages according to the production rules. If the newly derived age is not already in the graph, it will be added to the graph and to the work list. Otherwise, it will be discarded. The limitation is that the order of CFL-reachability solving, namely age processing, depends only on the order of elements in the work list rather than the features of the graph. This causes inefficiency, which is mainly brought by transitive redundancy. So what is transitive redundancy? In CFL-reachability for a non-terminal A, its transitivity manifests in productions A equals AA, A equals A star, or A equals A plus, and so on. Transitivity indicates that any two transitive relations from Vi to Vj and from Vj to Vk indicates a new one from Vi to Vk. Transitive relations are everywhere in program analysis. For example, most assignment instructions in programs are modeled as transitive relations. The property of transitive relations allow multiple ways to derive the same age. In this example, we have two ways to derive the age v1 a v4 from the path v1 a v2 a v3 a v4. We can either derive the age from the head to the tail, where the age v1 a v3 is derived first, or from the tail to the head, where the age v2 a v4 is derived first. Here is another example. According to the context-free grammar, there are four ways to derive OFV5. However, the age OFV5 only needs to be added to the graph once to make the reachability relation explicit. In most cases, The standard algorithm will trigger all the 4 ways, which means that there are at least 3 redundant derivations. According to our empirical results from 2 popular clients, namely value flow analysis and alias analysis, redundant derivations occupy over 95% of all derivations. Our insight is that if we keep track of the order of nodes and edges in transitive relations, we can determine an order so that each summary edge can be derived from a path in only one way. Thereby, the transitive redundancy is eliminated. For the first example, if we only consider inducing edges from the head to the tail, then the second way for deriving the edge v1, a, v4 can be discarded. Similarly, in the second example, by only inducing edges from the head to the tail, only the last way to derive the edge O, f, v5 is preserved. Although the insight is direct, developing a reliable approach is challenging. As shown in the following graph, in real problems, a node or an edge can reside in multiple paths, so there's not an universal order that can cover all the edge derivations in a graph while excluding all the redundancy. Our solution is to let derivations of different paths follow different orders, and the technique is comprised of a hybrid data structure and a partially ordered CFL-reachability algorithm. Our hybrid data structure is a spanning tree augmented adjacency list graph representation. In the adjacency list graph representation, for a node vi and a symbol x, we use 2 adjacency lists, pred x vi and circ x vi to store the predecessors and successors of vi with respect to edges labeled by x. To construct spanning trees, we classify the transitive edges labeled by A into 2 classes, primary edges and secondary edges. Specifically, if an edge is not derived via the production rule A equals AA, then it's a primary edge, otherwise it's a secondary edge. For each node vi and each transitive relation A, we assign vi a predecessor tree, P tree AVI, and a successor tree, S tree AVI. Both trees are rooted at vi and are comprised of only primary A edges. Since secondary edges can always be derived from primary edges, this tree structure excludes the redundant information caused by secondary edges. Here is a graph and the spanning trees for nodes from v0 to v4. We can see that the secondary edges like v4 a v0 and v0 a v2 are not included in the spanning trees. As depicted in the graph, we combine spanning trees with adjacency lists by letting the elements of adjacency lists be a pointer pointing to the corresponding nodes in spanning trees. Since the adjacency lists can be implemented by hash tables, such a data structure has the benefits of both hash tables and trees and is highly efficient for lookup, traversal, and update. Specifically, if we want to look up, we can use the adjacency list, and if we want to traverse and update, we can use the spanning trees. Then let's talk about the partially ordered CFL-reachability algorithm, which runs on the hybrid data structure. First, we have a method to derive edges using spanning trees, as algorithm 2 in the paper. Specifically, while processing an edge vi, x, vj, for each production rule x equals ax, we update the adjacency list pred x vj using the predecessor tree p tree avi. And for each production rule x equals xa, we update the adjacency list circ x vi using the successor tree s tree avj. Here is an example. While processing the edge v0 x v5 based on the production rule x equals ax, we traverse the predecessor tree p tree av0 from the root to the leaf and update the adjacency list pred x v5. Similarly, while processing the edge v2 x v5, we traverse the predecessor tree p3 a v2 and update the adjacency list print x v5. Notably, while the traversal of p3 a v2 goes to v0, as v0 is already in the adjacency list print x v5, the traversal stops. In this way, two redundant derivations caused by v3 and v4 are avoided. Here, stopping the traversal at v0 is safe because v3 and v4 must be added to print x v5 by another traversal, which doesn't stop at v0. Second, we have a dynamic construction method for spanning trees. Based on transitivity, the method traverses two spanning trees to update other spanning trees. Specifically, while processing an HVI AVJ where A is transitive, we traverse P3 AVI and S3 AVJ and update the successor trees of the nodes in P3 AVI and the predecessor trees of the nodes in S3 AVJ. Notably, while updating a spanning tree, the corresponding adjacency list is also updated, and the traversal of P3 AVI is nested in the traversal of S3 AVJ. Here is an example. While processing the age v2 AV3, we traverse P3 AV2 and S3 AV3 from the roots to the leaves, where the traversal of P3 AV2 is nested in the traversal of S3 AV3. During the traversal, we update the successor trees of v2, v1, v0, and the predecessor tree of v3. In this case, the traversal of P3 AV2 stops at v3 because v3 is already in P3 AV3. In this way, we avoid the redundant derivation caused by v4. After finishing an iteration of traversal of P3 AV2, the outer traversal of S3 AV3 moves from v3 to v0, starting another inner traversal of P3 AV2. This dynamic construction method stops when all the inner traversals of P3 AV2 and all the outer traversals of S3 AV3 are finished. We integrate the aforementioned two methods into an overall CFL-reachability solver as algorithm 4 in the paper. The only difference of our algorithm from the standard one is the scheme for processing an age. Specifically, while processing an age, we use the two spanning tree-based methods to handle the production rules such as x equals ax, x equals xa, and a equals aa, and handle the other productions in the same way of the standard algorithm. The paper also discusses some grammar-based optimizations of our algorithm. The key idea is to use spanning trees to reduce redundant derivations to the largest extent. In the paper, we evaluate our technique on context-sensitive value flow analysis and field-sensitive alias analysis, running on 10 C and C++ programs on the spec CPU 2017 benchmark set. The result is promising. We can see that our technique reduced over 97% of the derivations for both clients and achieved speedups larger than 19 times over the standard algorithm. We also compare our technique with other state-of-the-art CFL-reachability solvers and find that our technique is at least 3 times faster. From these two charts, we see that the computational redundancy, namely redundant derivations, is greatly reduced by our technique, which is depicted as the blue bars. This is the main reason for the significant speedups. Our partially ordered CFL-reachability solver is now publicly available. On one hand, the paper contains the technical details, including the design of data structure and pseudocodes of the algorithms. You can implement your version according to the paper. On the other hand, our implementation is released on GitHub, and further updates will also be released in the same repository. Welcome to download and use. Finally, thank you for listening.